Have you ever wished robots could just figure things out on their own? Like, even if they haven't been explicitly taught every single step, what if a machine could actually develop its own clever shortcuts? Today, we're diving into that very possibility. We're exploring the really fascinating world of robotic manipulation and a pretty revolutionary new approach to training them. Our source for this deep dive is a technical report hot off the presses, really called SimpleVLA-RL, Scaling VLA Training via Reinforcement Learning. And our mission today is simple. We want to pull out the most important, the most impactful breakthroughs from this research. We'll look at how this new method is shaking up robot learning, how it tackles some really tough, long-standing challenges, and even how it leads to these genuinely surprising, almost creative behaviors from the robots. So get ready for some serious aha moments, I think.
Absolutely. This research introduces something called SimpleVLA-RL. It's basically an efficient reinforcement learning framework designed specifically for vision language action models, VLAs. And what's really fascinating here, I think, is how it directly addresses these big problems in robotics. You know, not having enough training data and robots not being able to generalize what they learn. It's really about moving beyond just mimicking human actions and enabling robots to genuinely discover better ways to do things. And the results show it dramatically boosts performance, both in simulations and, crucially, in the real world.
Okay, so let's back up just a touch. Let's make sure we're all on the same page. VLA models, vision language action. Can you give us the quick rundown? We talk about them as the next-gen robot brains, right?
That's a good way to put it. They're the systems that allow a robot to first see its environment using cameras or other sensors. That's the vision part. Then they need to understand instructions, usually given in natural language, like, hey, can you pick up the red block? That's the language part. And finally, they have to translate that understanding into physical movements to actually perform the task, the action part. So yeah, it's this integration of seeing, understanding, and doing.
Got it. And traditionally, how have we trained these complex models?
Well, the standard approach has been this two-stage process. First, there is large-scale pre-training on huge data sets to give the model a general foundation. Then comes supervised fine-tuning, or SFT. This is where the robot learns specific tasks by essentially watching and imitating lots and lots of high-quality examples, usually trajectories recorded from a human controlling the robot. And look, this SFT method has definitely shown progress, no doubt, but it hits a pretty significant wall when we try to scale it up or apply it to more complex real-world situations.
Right, and those walls, those limitations, are exactly what this report digs into. They highlight two really big hurdles that SFT just struggles to overcome. And for anyone working in robotics or even investing in it, these are like fundamental bottlenecks. Yeah. The first one is data scarcity. You mentioned needing lots of examples for SFT. Well, to really scale it up effectively, you need a massive amount of these human-operated demonstrations. But getting that data, it's incredibly expensive, it takes a ton of time, and it's just plain difficult. The report mentions needing, and I'm quoting here, meticulously designed experimental scenarios, diverse manipulation objects, and skilled operators. Think about that. Imagine trying to get a human expert to guide a robot perfectly stacking, say, 50 different types of bowls in 100 different ways. It severely limits how much data you can get and how varied it is. It's just not practical at scale.
Exactly. It's a huge practical limitation.
And the second challenge they point out is poor generalization. So, robots trained with SFT, they often stumble when they encounter something even slightly different from their training data. This is called distribution shift.
Yeah.
So if they face, unseen tasks, environments, or objects, their performance just drops off a cliff.
Yeah, they might be brilliant at stacking those specific red blocks under those exact lights in the lab.
Right. But ask them to stack, blue cylinders on a surface that's maybe a tiny bit uneven, and suddenly they can't do it. They fail.
It's a brittleness problem.
And you can see immediately, if you're trying to build robots that can actually work reliably out in the real world, maybe in your home or a factory, this lack of adaptability is a massive roadblock. It keeps robots stuck in very controlled environments.
Precisely. So faced with these major roadblocks, researchers started looking for alternatives. And interestingly, inspiration came from recent progress in a related field, large reasoning models, or LRMs. These are advanced AI models, things like DeepSeek R1, that are really good at complex step-by-step problem solving, almost like they can reason through things. And what they found is that reinforcement learning RL could significantly boost the step-by-step reasoning abilities of these LRMs. So the natural question became, could RL do something similar for the step-by-step action planning of VLA models? Could it help robots think and adapt their actions in the physical world?
Okay, so that's the bridge. That insight is what led to SimpleVLA-RL, the core idea we're unpacking today. It's an RL framework, but one that's specifically tailored, specifically engineered for these VLA models. The research is built upon an existing RL framework, something called veRL, but they made key VLA-specific adaptations. Things like how trajectories are sampled, making it highly parallelizable for scalability, handling rendering across multiple simulated environments, and optimizing the way losses are calculated. It sounds like quite an engineering feat.
It really is, and it's important to stress you can't just take the RL techniques used for large language models and apply them directly to robots. It's trickier than that. You see, LLMs generate text, tokens, sequentially, right, but they don't really get immediate feedback from the environment based on each word they produce. VLA models, on the other hand, are constantly interacting with the physical world. They require these continuous, multi-round interactions. Every single action the robot takes changes the state of the world.
And the robot has to see that change, perceive it, and then decide its next action based on that real-time feedback.
Exactly. It's a closed-loop system. Act, observe, act, observe. This constant physical interaction makes applying RL much more complex than in the purely digital realm of language models.
Okay, that makes sense. Now, one thing that really jumped out at me from the report was how they handled rewards in this simple VLA-RL framework. It seems surprisingly simple.
It is, and that's actually one of its strengths. They use a straightforward binary reward system. The robot gets a 1 if it successfully completes the overall task, and a 0 if it fails. That's it.
No partial credit, no little hints along the way like, you're getting warmer.
Nope. It avoids those traditional, often really complex, handcrafted process rewards, where engineers try to define rewards for every little substep. Those can be brittle and hard to transfer between tasks.
So this simple outcome-level reward, just success or failure at the end, makes it more scalable and broadly applicable.
Precisely. It basically tells the robot, look, I don't care how you do it, just get the job done. And this forces the robot to explore different strategies to figure out what actually leads to success.
Okay, so a tailored RL framework combined with this simple reward structure. What were the results? Did it actually work?
Oh, it worked extremely well. SimpleVLA-RL achieves state-of-the-art SOTA performance on several standard benchmarks. For example, they took a strong existing model, OpenVLA-OFT, and applied SimpleVLA-RL. On the LIBERO benchmark, the success rate jumped from an already good 91% to an outstanding 99.1%.
Wow, okay. That's nearing perfection.
Pretty much. And on another benchmark, RoboTwin 2.0, the improvement was even more dramatic. Performance went from 38.3%, which was respectable, all the way up to 68.8%. That's roughly an 80% relative improvement.
An 80% jump, that's huge.
It is. And it outperformed other leading methods, like one called Zero. Even on really complex tasks that require many steps, long horizon tasks, SimpleVLA-RL consistently showed significant gains. It really seems to set a new bar.
Now, this next result you mentioned earlier really caught my eye, especially thinking back to that data scarcity problem. How does SimpleVLA-RL affect the need for human demonstrations?
This is where it gets really interesting, maybe even game-changing. SimpleVLA-RL dramatically reduces how much demonstration data you need. Get this. They ran experiments where they fine-tuned the base model, OpenVLA-OFT, using only a single human demonstration for each task. Just one example. They called this one trajectory SFT.
Okay, one example seems incredibly minimal. How did that perform?
On its own, with just SFT, not great, especially on harder tasks. On the LIBERO long benchmark, the success rate was only 17.3%.
Right, as you'd expect with so little data.
But then they added SimpleVLA-RL on top of that single demonstration SFT model. The success rate leaped from that 17.3% to 91.7%.
Wait, hold on. From 17% to over 91%, with RL added to just one initial demonstration.
Exactly. And here's the kicker. That 91.7% success rate actually beat the performance of the model trained using SFT with the full set of demonstration trajectories.
That's incredible. So RL didn't just compensate for the lack of data. It actually allowed the model to learn better than just copying lots of examples.
It really suggests that RL can unlock massive scaling for VLA training. You might only need a tiny amount of minimal demonstration data to bootstrap the process, and then RL can take over and find highly effective policies. Think about the cost and time savings.
Yeah, the implications are enormous. What about the other big challenge, generalization? How did SimpleVLA-RL fare when facing new situations?
It showed really strong generalization across multiple dimensions, things like different spatial configurations, object types, and task settings. It adapted well. This is a major advantage over standard SFT, which, as we discussed, often suffers from what the paper calls catastrophic forgetting. Basically, when an SFT model tries to learn a new task, it can sometimes completely forget how to do tasks it previously mastered.
Right, its performance on unseen tasks can just plummet.
Exactly. The report notes that SFT success rates actually dropped to 0% on some unseen LIBERO goal tasks. Just totally failed. But SimpleVLA-RL showed consistent improvement even on these unseen tasks. It seems much better at retaining its existing skills while learning new ones that also generalize well. This robustness is absolutely key for real-world deployment.
And speaking of the real world, did these improvements translate from simulation to actual physical robots? That sim-to-real gap is notoriously difficult.
That's often the million-dollar question in robotics. And yes, the policies trained with SimpleVLA-RL purely in simulation transferred effectively to real robots. And crucially, they achieved significant performance gains without needing any real robot data during the RL phase.
No real robot data at all for the RL part. That's impressive.
It is. On the RoboTwin 2.0 tasks, they saw the average real-world success rate improve from 17.5% with just SFT to 38.5% after adding SimpleVLA-RL trained only in Sim. And for one specific task, pick bottle, which requires really precise movements, the SFT-only model completely failed in the real-world 0% success. SimpleVLA-RL, again trained only in Sim, managed a 15% success rate. Still room for improvement, but going from 0 to non-zero is a big deal.
Absolutely. Getting any success on a hard task with zero real-world RL training is a huge step for making this practical. Less time spent calibrating and tuning on expensive physical hardware.
Okay, so we've seen better performance, less need for data, better generalization, and promising sim-to-real transfer. But then the report mentions something. Well, something that sounds almost like robot creativity, this pushcut phenomenon. What's that about?
Ah, yes, the pushcut. This was a really fascinating observation the researchers made during the RL training. They defined it as the policy discovering previously unseen patterns beyond those seen in the previous training process.
So the robot basically figures out a completely new way to do things, a way it was never shown.
Exactly. It's like the robot having its own little aha moment and finding a shortcut.
Okay, I need examples.
Right. So take the move can pot task. In all the human demonstrations provided for SFT, the strategy was always the same. Grasp the can, lift it, move it over, and place it down. Typical pick and place.
But the VLA model trained with SimpleVLA-RL. It autonomously discovers a more efficient solution. Instead of grasping, it just pushes the can directly across the table into the target spot.
It just slides it.
Yep. A push-driven shortcut, as they call it. It completely skips the grasping and lifting.
Huh. Okay, another example.
Sure. For a task called place A to B left-right, the goal is to move object A next to object B. Again, the demonstrations involved grasping A and placing it, but the RL-trained model, it learned to just nudge or push object A into the correct position next to B. Again, bypassing the grasp.
Wow. So why does this happen? Why does RL find these pushing shortcuts when SFT just sticks to grasping?
It boils down to the fundamental difference between the training methods. SFT is essentially imitation learning. It tries to replicate the exact patterns it saw in the demonstrations. If the demos always show grasping, the SFT model will learn to grasp.
It's just copying the teacher.
Right. But RL is driven by exploration and rewards. Remember that simple binary reward. It only cares if the can ends up in the right place, or if object A ends up next to object B. It doesn't care how it gets there.
Ah, so pushing works just as well as grasping for achieving the final goal state.
Exactly. So the RL agent has this much broader exploration space. It's free to try out different things, including pushing. And if pushing turns out to be quicker or more reliable for achieving that final success state, the RL process will reinforce that behavior.
So the robot isn't explicitly programmed to find shortcuts. It just discovers them because the reward signal gives it the freedom to explore beyond the demonstrated method. That's really cool. It feels less like programming and more like actual learning.
It does. It highlights that RL isn't just about optimizing a known solution. It can be about discovering fundamentally new and potentially better solutions.
Okay, simple VLA-RL sounds incredibly powerful, but is it foolproof? Doesn't always work. The report must mention some limitations or failure cases, right?
Oh, absolutely. It's not magic. The researchers were clear about its limitations, and they identified the initial capability of the base model, what they call the model priors, from the SFT stage as being really critical.
Okay, so the starting point matters. What happens if the base SFT model is just really bad at the task to begin with?
Well, they found a scenario they called the zero ability scenario. If the base model has literally zero initial ability on a task, like a 0% success rate after SFT, then adding RL on top completely fails. It doesn't improve at all.
Why not?
Because RL learns from success. If the robot never accidentally stumbles upon a successful trajectory, even just once, then every trajectory it generates gets a reward of 0.
And if all the rewards are 0, the RL algorithm has no signal, nothing to learn from. It doesn't know which actions were slightly better or worse because everything just looks like failure.
Exactly. It's like trying to learn to ride a bike if you instantly fall off every single time you try it without ever even getting a tiny bit of balance. There's no positive feedback to build on.
So you need some minimal level of competence for RL to even get started.
Precisely. The report emphasizes that RL effectiveness has a threshold. You need at least a small chance of succeeding occasionally for the RL exploration to find those successful pathways and reinforce them. Stronger initial abilities, meaning a better starting SFT model, provide more effective launch points for RL exploration. This leads to much bigger improvements.
Do they give numbers on that?
They do. For one task, a model that started with only a 1.2% success rate after SFT only improved to 4.3% after RL. Not much gain. But for the same task, a different model that started with a much better 29.7% success rate after SFT, RL boosted that all the way up to 68.3%.
Wow. Okay, so RL is like an amplifier. It works best when it has something decent to amplify in the first place. It can't create competence out of absolutely nothing.
That's a great way to put it. It amplifies existing ability. It doesn't conjure it from thin air. That's a really important practical consideration for anyone looking to implement this.
Okay, what a fascinating journey through this research. We started by looking at those really significant hurdles for VLA models, needing tons of data, struggling to generalize. And we've seen how this simple VLA-RL approach, using reinforcement learning smartly, seems to directly tackle them. I mean, boosting performance so dramatically, especially with minimal demonstration data, and enabling that sim-to-real transfer without needing real robot tuning, that feels like a really significant leap forward, doesn't it?
It really does seem like a major step, and if we zoom out a bit, connect this to the bigger picture, that pushcut phenomenon is particularly thought-provoking. It really highlights the power of RL, not just for optimization, but for genuine discovery, finding completely new strategies that maybe even a human expert wouldn't have thought of for that specific robot setup. It hints at this future where our autonomous systems aren't just following instructions, but are actively problem-solving, maybe even innovating in their environments. And that raises some big questions,
Like what?
Well, what does it really mean for the future of robotics, and maybe even AI more broadly, when machines can autonomously develop more efficient, sometimes unexpected, never-before-seen strategies to achieve goals? How does that change the game?
That's a powerful thought to end on. This research definitely makes you wonder, if robots can discover pushcuts today, what other completely novel patterns, what other unexpected efficiencies or solutions might they uncover tomorrow if we give them the freedom to explore through reinforcement learning? How might that shift our relationship with intelligent machines, maybe moving beyond seeing them just as tools that execute our commands towards viewing them as potential, genuine innovators? Lots to think about there.